Welcome to our deep dive all about machine learning. You sent in a really interesting mix of sources, and it seems like you're trying to get a good grasp on all those fundamentals. I mean, we've got core concepts, algorithms, and even a peek into some advanced stuff. Sounds like you're building a machine learning cheat sheet, which is, well, exactly what we aim to do today.
Yeah, smart move starting with the foundations. There's so much hype surrounding machine learning these days, but if you understand the history and the core principles, you can cut through the noise, get a much clearer view of what it can really do.
Speaking of history, one thing that really struck me was, well, the fact that the term machine learning was coined way back in 1959, possibly as a marketing tactic by IBM. I mean, it's kind of wild, right? Makes you wonder how much of what we see today is real progress versus just, clever branding.
It definitely shows you how science and marketing, they're intertwined, even in a complex field like machine learning. It's a reminder that progress takes time, and big breakthroughs, they often build on like decades of research, even if they're presented as these sudden revolutions.
Definitely makes you think twice about all those flashy headlines. So let's get into those core concepts. The book clearly distinguished between supervised and unsupervised learning, using some really cool examples like playing video games and detecting cancer. Those really helped bring the ideas to life.
Those examples are great. A great way to understand the key difference, whether the algorithm gets labeled data while it's training. Think of supervised learning like having a teacher guiding you. You're given data with the right answers, and you learn to connect inputs to outputs. Like in that video game example, you could feed the algorithm data on a player's actions and what happens, like whether they win or lose.
So supervised learning, it's all about learning from examples, kind of like when you study for a test by reviewing past problems.
Yeah, exactly. The algorithm learns by example, figures out the rules and patterns that connect the input and the output. Now, unsupervised learning, that's more like being dropped in a new city without a map. You have to figure out the neighborhoods, the landmarks, just by observing and exploring.
I love that. Unsupervised learning is like being a detective, piecing clues together to find hidden patterns. No one's telling you what to look for.
Precisely. In unsupervised learning, you give the algorithm data without labels, and it's up to it to find patterns or structures. Take the cancer detection example. You might give the algorithm a bunch of patient scans, and it has to identify clusters or anomalies that could point to cancer. It's about making sense of the data without being told what's right or wrong.
This brings up an interesting question. How do we choose which type of learning to use for a specific problem?
That's where it's crucial to understand your data and what you're trying to solve. If you have labeled data and you want to make predictions or classify data, supervised learning is the way to go. But if your data is unlabeled and you're more interested in finding those hidden patterns or grouping similar data points, then unsupervised learning might be a better fit.
It's like picking the right tool for the job. You wouldn't use a hammer to screw in a light bulb, right? Now let's move on to the tools of the trade, the algorithms. The book covered some fundamental ones like linear and logistic regression, decision trees, support vector machines or SVMs, and k-nearest neighbors.
Each of these algorithms has its own strengths and weaknesses. So understanding how they work is key to choosing the right one. Let's start with linear regression. It's great for predicting continuous values, things like stock prices or sales figures. It works on the idea that there's a linear relationship between the input features and the output you want to predict.
So it's like drawing a straight line through a scatter plot, trying to find the line that best fits the overall trend.
Exactly. But sometimes a straight line doesn't cut it. You need something to handle the complexity of the data, and that's where decision trees come in. They handle nonlinear relationships really well, and they're easier to understand than some other algorithms.
The book described decision trees as working by splitting the data based on feature values, creating a tree-like structure that leads to a prediction. They seem like a more intuitive way to model complex decision-making.
They are, in a way. Think of it like a game of 20 questions. Each question helps you narrow down the possibilities until you get the answer. Decision trees work similarly, using a series of if-then-else statements to divide the data and make a prediction.
Now, what about SVMs? They seem a little more mysterious.
Imagine you're trying to separate two groups of, let's say, photos of cats and dogs. SVMs are like drawing the perfect line to divide them, but it's not just a simple line. They can create complex boundaries, making them super powerful. That's where the kernel trick comes in. It's like giving the algorithm extra dimensions to work with.
Kernel trick sounds like something out of a sci-fi movie. It's amazing how these algorithms handle such complex data. What about key nearest neighbors? That one seems more straightforward.
It is, in a way. K-nearest neighbors, or KNN, is all about wisdom of the crowd. So picture your data points plotted in space. KNN looks at the K closest points, the neighbors, to a new data point, and predicts its class based on those neighbors. It's like asking your friends for advice. The more similar they are to you, the more you trust them.
So it's about finding the most similar data points and using them to make predictions.
Exactly. Simple idea, but very effective, especially for classification tasks where you want to put a data point into a category based on its similarity to others.
With all these powerful algorithms, it's tempting to think more complex is always better. But the book warned about overfitting, when a model learns the training data too well and ends up, memorizing the noise instead of the real patterns. They use this great analogy of a polynomial regression line wiggling to fit every point, which helped me really picture the problem.
That analogy is spot on. It's like a student who memorizes test answers without understanding the concepts. They'll fail on new questions. An overfit model does poorly with unseen data because it hasn't learned the general patterns, just the quirks of the training data.
So how do we stop our models from overachieving in a bad way?
Regularization is a key technique. It's like adding weights to that wiggling line, forcing it to smooth out and capture the bigger trend. It basically stops the model from getting too complex and helps it focus on the important patterns.
So regularization is about finding that sweet spot between complexity and simplicity.
Exactly. We want models that capture the patterns in the data without getting bogged down by noise and losing their ability to generalize to new data.
Now, with all these different algorithms, how do we pick the right one?
That's the million-dollar question. There's no single answer. It often involves trial and error, testing different algorithms, and seeing how they do on data the model hasn't seen before.
So it's like being a detective again, but this time we're trying to find the best algorithm, like testing different leads and seeing which one leads to the most accurate predictions.
That's it. It's about experimenting and exploring, considering things like whether your data has labels, what type of problem you're solving, and even the computing power you have.
It sounds like the key to machine learning is being adaptable, willing to try different things and find what works best for each problem.
Absolutely. It's about being a scientist and an artist, combining technical know-how with creativity and intuition.
Before we jump into the advanced stuff, let's recap what we've learned about the fundamentals. What are the most important takeaways so far?
I'd say it comes down to this. Machine learning is a powerful set of tools with a long history and a bunch of different algorithms. Understanding the basics, like supervised versus unsupervised learning, the different types of algorithms and the dangers of overfitting, is key to using these techniques effectively. It's all about picking the right tool for the job and using it wisely.
I'm already feeling more confident about navigating this complex world. Now, I'm particularly excited about the next section on neural networks and deep learning. This is where things get really futuristic.
I know, right? What's so cool about deep learning is its ability to extract complex features and patterns from raw data, mimicking how our brains process information. It's what's driving those breakthroughs in image recognition, natural language processing, even self-driving cars.
That's where it gets really interesting. The book mentioned a simple neural network is basically a generalization of logistic regression, which we already talked about. It's like we're building on what we've already learned.
Yes, and that's a great way to start understanding deep learning. Think of a neural network as a web of connected nodes, arranged in layers. Each node does a simple calculation, and the connections let information flow through the network. The deep part means there are multiple hidden layers between the input and output, which lets the network learn increasingly abstract representations of the data.
I can already picture all those nodes firing away, learning from the data. But before we get lost in the neural forest, what makes deep learning so powerful?
One key concept is hierarchical feature learning. As data moves through the layers of a deep neural network, the network learns to extract features that are more and more complex. Early layers might pick up simple things like edges or textures, while deeper layers combine those to recognize complex patterns, like shapes or even objects.
So it's like building a tower of knowledge, each layer adding a new level of understanding.
Exactly. This hierarchical learning is what makes deep learning excel at tasks that traditional machine learning algorithms find really hard.
Okay, let's talk about some specific types of neural networks that stood out to me in the book. Convolutional neural networks, CNNs, and recurrent neural networks, RNNs, sound especially intriguing. What makes them special?
CNNs are perfect for image and video processing. They use a special type of layer called a convolutional layer, which scans the image with small filters, picking out local features like edges and textures. It's like looking at an image through a magnifying glass, focusing on details, and then putting them together to understand the whole picture.
So it's like having a team of experts, each focusing on a different part of the image and then working together to get a complete understanding.
That's a great way to put it. And then we have RNNs, which are made for sequential data like text or time series. They can process information in order, keeping an internal state or memory that captures the context of previous inputs.
So RNNs are like the storytellers of the neural network world.
Exactly. They're awesome at natural language processing, where a word's meaning depends on the words before it. Just like you wouldn't understand a sentence by reading each word alone, RNNs get the sequence step by step, considering the context.
This is all fascinating, but I have to admit, my brain is getting a bit overloaded. It's like drinking from a fire hose.
Uh-huh. Deep learning can feel like that sometimes, but it's a fire hose of amazing stuff. Start with the basics and gradually build your understanding. Don't be afraid to ask questions and take your time absorbing these concepts.
That's good to hear. I'm starting to see that deep learning isn't about memorizing complex stuff. It's about understanding how these tools work and how to use them effectively.
You got it. It's about developing an intuition for how these networks learn and what kinds of problems they're good at solving. It's about staying curious and exploring this always evolving landscape.
Well said. I'm definitely curious to learn more about some of those advanced techniques mentioned in the book, like transfer learning, self-supervised learning, and metric learning. They sound like they're pushing the boundaries of what's possible with machine learning.
I think you'll find them pretty interesting. They're a big leap forward, opening up exciting new possibilities.
Sounds like we have a lot more ground to cover. Before we dive into those advanced techniques, let's quickly recap what we've learned about neural networks and deep learning.
Great idea. So we've established that deep learning is about training artificial neural networks of interconnected nodes organized in layers to learn from data. The deep part refers to those multiple hidden layers, which enable hierarchical feature learning, giving deep learning its power to extract complex patterns from raw data.
We also explored two key types: convolutional neural networks, or CNNs, which excel at image processing, and recurrent neural networks, or RNNs, which handle sequential data like text or time series.
Right. CNNs use those special convolutional layers to scan the input data, extracting local features and piecing them together, while RNNs have an internal state that allows them to process information sequentially, keeping track of the context.
This brings us to the cutting edge of machine learning, those advanced techniques that are pushing the boundaries. The book briefly mentioned things like transfer learning, self-supervised learning, and metric learning.
These techniques are a major step forward, allowing us to tackle increasingly complex problems and achieve even better performance. They're really changing the game.
Let's start with transfer learning. It almost sounds like science fiction transferring knowledge from one model to another. How does that actually work?
It might sound like magic, but it's based on a simple observation. Many machine learning tasks have common features. Take image recognition. Whether it's cats, cars, or galaxies, the early layers of a neural network often learn similar things like edges, textures, and basic shapes.
So instead of starting from scratch, we can use these pre-trained models that have already learned those fundamental features.
Exactly. Transfer learning lets us use a model trained on a huge data set, like ImageNet, and adapt it to a specific task, even with a smaller data set. It's like having a pro chef and teaching them a new recipe. They already have the skills, so they can master the new dish quickly.
What a great analogy. It's like giving our model a crash course using the knowledge of its predecessors. How do we adapt that pre-trained model to a specific task?
One common technique is fine-tuning, where we take the pre-trained model and retrain some of its layers on our new data. It's like letting that chef experiment with the new recipe, making adjustments while still using their expertise.
This fine-tuning process is fascinating. Are there any times when transfer learning isn't the best approach?
That's a good question. Like many things in machine learning, it depends. Transfer learning works best when the original task and the new task are related. If you try to take a model trained on images and use it for text, it's probably not going to work.
So it's like asking that chef to write poetry. Their cooking skills won't transfer well to the world of words.
Exactly. Choose a pre-trained model that's relevant to your task and fine-tune it carefully to make sure it adapts to your specific data.
Okay, now on to self-supervised learning. The name itself is a bit of a paradox. How can a model learn without any guidance?
It's all about designing tasks where the model learns from the data's structure without needing labels. Remember that word embedding example? That's a classic case of self-supervised learning.
You mean where the model learns to predict a word's context from the words around it?
Exactly, like a word game filling in the blanks. In doing this, the model learns to represent words as vectors that capture meaning. Similar words end up with similar vector representations.
It's as if the model teaches itself a new language just by observing how words are used in real-world examples.
Precisely. This self-supervised approach is great for learning representations from all kinds of data, not just text. You can train a model to predict missing pieces of an image, or even the next frame in a video.
It's like solving a puzzle, using the existing pieces to figure out what's missing. What are some real-world uses for this type of learning?
It's really promising in areas where labeled data is hard to get or expensive. By using the huge amounts of unlabeled data out there, self-supervised learning can help us train models for tasks that we couldn't before. It's also opening up new possibilities in robotics and self-driving cars, where models need to learn about the world without constant human input.
This all sounds very promising. It seems like self-supervised learning could unlock a whole new level of machine learning capabilities.
Absolutely. It's an area that's being actively researched, and we're only just beginning to tap into its potential. Now let's move on to the third advanced technique, metric learning. As we mentioned earlier, it involves learning a custom way to measure distance that's tailored to a specific task.
Right, because those standard metrics, like Euclidean distance, might not always capture the important similarities or differences between data points. They can be a bit too general.
Exactly. Think about face recognition. Two faces might look very similar, pixel by pixel, but be completely different people. Metric learning lets us teach the model which features are most important for telling different classes apart.
It's like giving the model a specialized set of rules for measuring similarity, rules that are custom-made for a particular area.
Precisely. And this custom metric can drastically improve tasks like clustering or classification. Imagine you're building a system to recommend products to customers. If you can learn a metric that captures what makes products similar in the eyes of your customers, you can make much better recommendations.
That makes a lot of sense. It's like teaching the model to see the world through the eyes of our customers, understanding what features are most important to them.
Exactly. This ability to customize the metric is what makes metric learning so powerful. It goes beyond those predefined metrics and lets us tailor the model to the specific details of our task.
These advanced techniques are truly eye-opening. We're moving beyond simply training models to predict or classify. We're teaching them to learn and adapt in ways that were once unimaginable.
I agree. It feels like we're at the beginning of a new era in artificial intelligence. But it's important to remember that even with these advancements, there are still challenges and limitations.
That's a crucial point. The book highlighted some of these, like data quality, bias, and the need for explainability. We can't forget about responsible AI development, even with all these sophisticated techniques.
You're absolutely right. Let's delve into those challenges and see how we can address them.
Let's start with data quality, which keeps coming up in our conversation. We've said that if our training data is flawed or biased, our models will inherit those flaws. It's like building a house on a weak foundation. No matter how beautiful it is, it won't last.
That's a perfect analogy. Data quality is fundamental in machine learning. If our data is incomplete, inaccurate, or biased, our models will reflect that and could make unfair or discriminatory predictions.
So it's not enough to just feed our algorithms tons of data. We need to be very careful about where that data comes from and how it was collected.
Exactly. We need to be aware of potential biases and work to reduce them. This might involve carefully choosing our data sets to make sure they include different perspectives, or even developing techniques that can spot incorrect biases in the data.
It sounds like machine learning practitioners have a big responsibility. We're not just data scientists, we're also data ethicists.
I think that's a fair point. As machine learning becomes more advanced, we need to think more and more about the ethical implications of our work.
Now, let's talk about explainability, which we mentioned earlier. Some machine learning models, especially deep neural networks, can be incredibly complex and hard to understand. This lack of transparency is a problem in areas where trust and accountability are essential.
You're absolutely right. Imagine a machine learning model making decisions about loans or medical diagnoses. If we don't understand why it's making certain choices, it's hard to trust its judgment or hold it responsible.
It's like being told to follow instructions without knowing the reason behind them. You'd probably be hesitant, especially if the stakes were high.
Exactly. That's why there's a growing movement toward developing machine learning models that are easier to understand, models where we can see why they're making certain predictions. This is crucial for building trust and making sure these systems are used fairly.
It's like having a clear explanation along with those instructions. You can see the logic and feel more confident in following them.
Precisely. Interpretability is key to building trust in these systems and ensuring they're used fairly and ethically.
Another challenge we briefly touched upon was hyperparameter tuning. It can feel like a guessing game, trying to find the best settings for our algorithms. Like tuning a musical instrument, you have all these knobs and dials, but finding the perfect combination can be really tricky and time-consuming.
It's a balancing act, that's for sure. You're trying to find the settings where your model works well without memorizing the training data too closely. It often takes a lot of experimentation, trial and error, and a good understanding of how the algorithms work.
Sounds like a mix of science and art.
Yeah, exactly. We talked about techniques like grid search and cross-validation, which can help us systematically try different settings, but it still takes patience and attention to detail.
It's like detective work, isn't it? We have to carefully look at the evidence, learn from our experiments, and use our judgment to find the best settings.
I like that comparison. It shows how important both analytical skills and a willingness to adapt are in this process.
So, with all these advancements and challenges, what do you think the future holds for machine learning? Where do you see the field going?
That's a great question, and it's one that sparks a lot of excitement and speculation. I think we'll see more and more breakthroughs in areas like natural language processing, computer vision, and robotics. Machines will get better at understanding and interacting with the world in ways that were once thought to be exclusively human.
It's almost like we're witnessing the emergence of a new kind of intelligence, one that isn't limited by human biology.
That's a thought-provoking idea. It raises questions about what it means for a machine to be intelligent, and how these advancements in AI will change our understanding of ourselves.
Now we're getting into deep philosophical waters. But there are important questions to consider as machines become more sophisticated.
Absolutely. We need to approach these advancements with both excitement and a sense of responsibility. We need to make sure these powerful technologies are used for good, to solve problems, and make lives better. We need to be aware of the potential risks and work to reduce them.
It's like we're explorers venturing into uncharted territory. We're driven by curiosity and a desire to push the limits of what's possible, but we also need to be careful to make sure that our explorations benefit humanity.
Well said. It's a delicate balance, but one that we can achieve by working together, having open discussions, and sharing a commitment to using these powerful technologies to make the world a better place.
Now, let's dive into the world of unsupervised learning, where things get more exploratory. We're dealing with unlabeled data and trying to discover hidden patterns and structures.
It's like being a detective without all the clues, trying to piece together a mystery. We're trying to make sense of the data on our own, without any explicit instructions.
So instead of having a teacher giving us the right answers, we're trying to make sense of the data on our own.
Exactly. This can be really powerful for tasks like clustering, where you group similar data points together, or anomaly detection, where you find unusual or unexpected data points.
The book mentioned a few algorithms for unsupervised learning, like k-means clustering, DBSCAN, and Gaussian mixture models. Can you give us a quick overview of how those work and what they're good at?
Let's start with k-means clustering, which is one of the most popular ones. The goal is to divide the data into k clusters, where k is a number we choose beforehand.
So it's like dividing a group of people into teams based on how similar they are.
Exactly. The algorithm works by repeatedly assigning data points to the nearest cluster center, and then updating the centers based on the average location of the points in each cluster. It's like finding the best meeting spots for groups of people based on where they live.
That's a great way to explain it. What about DBSCAN? How is it different?
DBSCAN, which stands for Density-Based Spatial Clustering of Applications with Noise, finds clusters based on how densely packed the data points are in different areas. And we don't have to tell it how many clusters to look for.
So it's like identifying neighborhoods in a city based on where the houses or buildings are concentrated.
Precisely. DBSCAN looks for areas where the data points are close together, separated by areas where they're more spread out. It can also handle outliers, those data points that don't fit into any cluster, by recognizing them as noise.
That's impressive. It's like the algorithm filters out the distractions and focuses on the meaningful patterns in the data.
Then we have Gaussian mixture models, or GMMs, which assume that the data comes from a combination of Gaussian distributions, which are those bell-shaped curves you might remember from statistics.
Ah, yes. I remember those from my stats class.
GMMs try to find the best set of Gaussian distributions that fit the data. which lets us model complex data patterns and identify clusters even when they overlap or have unusual shapes.
So it's like trying to fit different sized and shaped bells to the data to capture the different groups.
That's a great way to picture it. GMLs can also tell us how likely a data point is to belong to each cluster, which is useful when we need to measure uncertainty.
These unsupervised learning algorithms are impressive. It's amazing how they can find hidden patterns and structures in data without any guidance.
They are, and they're used in many areas like customer segmentation, anomaly detection, and even image and speech recognition.
Now let's discuss dimensionality reduction, which is closely related to unsupervised learning. The book mentioned PCA and UMP as common methods for reducing the number of features in our data.
Dimensionality reduction is a great way to simplify data and make it easier to analyze or visualize. It's about finding a way to represent the data using fewer dimensions while keeping the most important information.
So it's like compressing a higher resolution image to make the file size smaller, but still keeping the essential details.
Perfect analogy. PCA, or principal component analysis, is one of those widely used techniques. It finds the directions, or principal components, that capture the most variation in the data.
So it's like finding the directions in the data where the points are most spread out.
Exactly. By projecting the data onto those directions, we can reduce the number of dimensions while still preserving the most important information.
And how is UMAP different from PCA?
UMAP, which stands for Uniform Manifold Approximation and Projection, is a newer technique that often does a better job than PCA, especially for visualizing high-dimensional data. It tries to keep both the overall structure of the data and the local relationships between data points.
So it's like creating a map that shows both the big picture and the detailed streets and landmarks.
That's a great way to visualize it. Yeah. UMAP can create beautiful and informative visualizations that reveal hidden structures in data, structures that were hard to see before.
Dimensionality reduction sounds incredibly useful, but are there any downsides or things we should be careful about?
One thing to keep in mind is that whenever we reduce the dimensions of our data, we're losing some information. We're trading some detail for simplicity. So it's important to choose the right technique, one that keeps the information that's most relevant to our task.
It's like choosing the right level of compression for an image. We want to make the file smaller, but we don't want to lose too much quality in the process.
Exactly. Another thing to consider is that the new representation of the data, after we've reduced the dimensions, might not be easy to interpret. It might not be clear what the new features represent in terms of the original ones.
So there's a trade-off between simplicity and interpretability.
In a way, yes. But even if the new representation isn't easy to interpret, it can still be useful for tasks like clustering, classification, or visualization.
Okay, let's switch gears again and talk about outlier detection, which is especially relevant to unsupervised learning. The book mentioned techniques like one-class classification and autoencoders.
Outlier detection is about finding those unusual or unexpected data points, the ones that don't fit the normal patterns. It's like finding a needle in a haystack or spotting the odd one out in a crowd.
So it's about finding anomalies, the data points that are different from the norm.
Exactly. This is really useful for tasks like fraud detection, intrusion detection, or quality control.
How do one-class classification and autoencoders work for outlier detection?
One-class classification involves training a model to recognize the normal data points, and then using that model to identify any new data points that are outside of what the model considers normal.
So it's like drawing a boundary around the normal data points, and anything outside of that boundary is considered an outlier.
That's a good analogy. Autoencoders, which we talked about earlier with deep learning, can also be used for outlier detection. Remember that autoencoders are trained to reconstruct their input. If we train an autoencoder on normal data, it will have trouble reconstructing outlier data points.
So it's like trying to fit a square peg into a round hole. The autoencoder won't be able to reconstruct data that doesn't match what it's learned about normal data.
Exactly. By measuring how well the autoencoder reconstructs the data, that is, the difference between the original data and the reconstructed data, we could identify potential outliers. The data points that the autoencoder struggles to reconstruct are likely to be the unusual ones.
These outlier detection techniques sound incredibly useful for a lot of different applications. It's like having a watchful eye that can spot the unusual events and help us prevent fraud, intrusions, or other problems.
Absolutely. As we deal with more and more data, outlier detection will become even more important for ensuring data quality and security.
We've covered a lot in this deep dive, from the basics of machine learning to those advanced techniques like transfer learning and self-supervised learning. We've explored supervised and unsupervised learning, delved into deep neural networks, and touched upon how this fascinating field is constantly changing.
And we've seen that machine learning is a rapidly advancing field, with new techniques and applications emerging all the time. It's a field full of promise and challenges, one that will continue to shape our world in profound ways.
I'm feeling a bit overwhelmed by all the information, but also incredibly inspired by all the possibilities. It's like we've taken a whirlwind tour through the world of machine learning, and I'm eager to continue exploring.
I know what you mean. It's a vast and complex field, but it's also incredibly rewarding. And the learning never really stops.
Well said. Before we move on to the next part of our deep dive, I want to emphasize something the book mentioned: the importance of experimentation and exploration in machine learning.
Absolutely. Machine learning isn't just about memorizing algorithms. It's about developing an intuition for how these algorithms work and knowing how to apply them to real-world problems. And that comes from experience, from trying things out, making mistakes, and learning from them.
So it's about embracing the trial and error process, being willing to experiment and push the boundaries.
Exactly. That's what makes this field so exciting. There's always something new to learn, a new problem to solve, a new discovery waiting to be made.
That's a great place to pause for now. Join us for part 2 of this deep dive, where we'll continue our exploration of machine learning.
So, picking up where we left off, let's dive a little deeper into those advanced techniques, starting with transfer learning.
Perfect, because I'm still trying to wrap my head around how we actually transfer learning from one model to another. It sounds, well, almost magical.
It might sound that way, but it's actually based on a pretty practical observation. Many machine learning tasks, they share some common features. Think about image recognition. Whether you're identifying cats, cars, or even galaxies, on the early layers of a neural network, they often learn similar things, like edges, textures, basic shapes.
So instead of starting from scratch every time, we can use these pre-trained models that have already learned those fundamental building blocks.
Exactly. Transfer learning lets us take a model that's been trained on a massive data set, like ImageNet, which has millions of labeled images, and we can adapt it to our specific task, even if our own data set is much smaller. It's like, imagine taking a seasoned musician and giving them a new instrument. They already have the core musical knowledge, so they pick up the new instrument really quickly.
I love that analogy. It's like giving our model a fast track to expertise, using the knowledge gained from like this huge library of experience. But how do we actually adapt that pre-trained model to our specific task?
Yeah. Well, there are a few different ways. One common technique is called fine-tuning, where we retrain some of the layers of that pre-trained model on our new data. So it's like taking that seasoned musician and letting them, jam with the new instrument, improvise, and find their own style, but they're still drawing on those fundamental musical skills.
Precisely. And this fine-tuning process can be really effective, often getting state-of-the-art results with much less data and computing power than if we trained a model from scratch.
Exactly. It's a much more efficient approach.
This is incredible, but it makes me wonder about the limits of transfer learning, right? Are there cases where it doesn't work so well?
That's a great point. And the answer, like with many things in machine learning, is, well, it depends. Transfer learning works best when the original task and the new task, they have some things in common. So for instance, a model that's trained to recognize objects in general, it'll likely do well if you adapt it to recognizing specific types of objects. But if you try to take a model that's been trained on images and apply it to a task with text data, is probably not going to be very successful.
It's like asking that musician to suddenly become a painter.
Oh.
Their musical talents might not translate very well to the visual arts.
Exactly. The key is to choose a pre-trained model that's relevant to the task you're working on, and then to fine-tune it carefully to make sure it adapts well to the specifics of your data.
Okay, so now let's move on to self-supervised learning. This concept, it still feels a little mysterious to me. How can a model actually learn without any external guidance?
It's all about setting up clever tasks where the model can learn from the structure of the data itself. Remember that word embedding example we talked about, where the model learns to predict a word's context based on the words that surround it?
Right. It's like that word game where you have to fill in the blank based on the surrounding sentences.
Exactly. And in the process of playing this game, the model learns to represent words as vectors that capture their semantic meaning. So words that appear in similar contexts end up having similar vector representations.
It's fascinating. It's almost as if the model is teaching itself a new language by observing how words are used in their natural environment.
That's a great way to put it. And this self-supervised approach has been really successful for learning representations of all sorts of data, not just text. You can train a model to predict missing parts of an image, or even the next frame in a video sequence.
It's like those brain teaser puzzles where you have to figure out the missing piece based on the patterns that you see. So what are some real-world applications for this kind of learning?
Well, one really exciting area is in domains where labeled data is really hard to come by or very expensive to collect. Self-supervised learning lets us train models for tasks that were basically impossible before. And it's also opening up new possibilities in robotics and autonomous driving, where the models need to learn to interact with the world without constant human supervision.
It's like giving these machines the ability to learn from their own experiences, much like humans do. That's pretty remarkable. Now let's move on to metric learning. We touched on it earlier. It's about learning a custom distance function that's specifically designed for the task at hand.
You got it. Those standard metrics like Euclidean distance, they don't always capture those subtle differences in similarity between data points. They're kind of like a one-size-fits-all solution. And as we know, one size doesn't always fit.
Right. It's like trying to measure the distance between two cities using just a straight ruler. You'd completely miss all those curves and turns of the actual roads that connect them.
Exactly. With metric learning, we're actually teaching the model what features are really important for distinguishing between different classes. So for example, in face recognition, two faces, they might be quite similar in terms of their pixel values, but they represent two totally different people. Metric learning helps us focus on those features that really define individual identity.
So it's like giving the model a customized map that highlights all the important landmarks for navigating a specific area.
Precisely. And this tailored approach, it can really improve the performance of tasks like clustering or classification. Imagine you're building a recommendation system for music. If we can learn a metric that captures a user's taste in music based on their listening history, we can recommend new artists and songs that they'll actually enjoy.
It's like having a friend who knows your musical preferences really, really well and can always recommend something new and exciting that you'll love.
Exactly. That's the beauty of metric learning.
Yeah.
It lets us go beyond those generic measures of similarity and create models that really understand the nuances of specific domains.
These advanced techniques, they're really impressive. It feels like we're seeing a whole new paradigm shift in machine learning. We're not just teaching models to make predictions, we're giving them the tools to actually learn and adapt in ways that were previously unthinkable.
I agree. It's like we're at the beginning of a new era in artificial intelligence. But it's important to remember that while these advancements are exciting, they also come with challenges and limitations.
That's a really crucial point. The book highlighted some of these, like data quality, bias, and the need for explainability. Even with all these sophisticated techniques, we can't lose sight of the importance of responsible AI development.
You're absolutely right. Let's take a closer look at those challenges and see how we can try to address them.
Okay, so let's start with data quality, which seems to be a recurring theme in our conversation. As we've said before, if our training data is flawed or biased, our models, they're going to inherit those flaws. It's like building a house on a shaky foundation. No matter how beautiful the house is, it's not going to last very long.
That's a great analogy. Data quality is absolutely essential in machine learning. If our data is incomplete, inaccurate, or biased, our models will reflect those shortcomings. And that could lead to unfair or discriminatory predictions.
So it's not just about feeding massive amounts of data into our algorithms. We need to be very careful about where that data comes from and how it was collected.
Exactly. We need to be very aware of potential biases in the data and take steps to mitigate them. So that might involve carefully curating our data sets to make sure they represent diverse perspectives or developing techniques that can actually identify and correct for biases in the data.
It sounds like a lot of responsibility rests on the shoulders of machine learning practitioners. We're not just data scientists. We're also data ethicists.
I think that's a fair assessment. As the field of machine learning continues to mature, we need to be increasingly mindful of the ethical implications of our work.
Now let's talk about explainability. We mentioned this before, but some models, especially deep neural networks, they can be incredibly complex and hard to interpret. And this lack of transparency, well, it can be a real obstacle in areas where trust and accountability are essential.
You're right. Imagine a scenario where a machine learning model is being used to make decisions about loan applications or medical diagnoses.
Yeah.
If we don't understand why the model is making certain predictions, it's really hard to trust its judgment or hold it accountable for its decisions.
It's like being told to follow a set of instructions without knowing the reasoning behind them. You might be hesitant to follow those instructions, especially if the stakes are high.
Yeah. Exactly. And that's why there's this growing emphasis on developing more interpretable machine learning models where we can actually understand the logic driving their predictions.
So it's like having a clear explanation along with those instructions. You can see the thought process behind the decisions and feel more confident in following them.
Precisely. Interpretability is essential for building trust in machine learning systems and ensuring that these systems are used fairly and ethically.
Another challenge that we talked about briefly was hyperparameter tuning. It can feel like a bit of a black art trying to find the optimal settings for our algorithms. It's like trying to tune a musical instrument. You've got all these knobs and dials, but finding the perfect combination to produce the desired sound, it can be a really time-consuming and intricate process.
It is. It's a real balancing act. You're trying to find the sweet spot where your model performs well without overfitting to the data. It often involves a lot of experimentation, trial and error, and a good understanding of the algorithms you're working with.
So it sounds like a blend of scientific rigor and artistic intuition.
Exactly. And we discussed earlier, there are techniques like grid search and cross-validation that can help us systematically explore different hyperparameter settings. But it's still an area that often requires a lot of patience and a careful attention to detail.
It's like being a detective searching for clues, isn't it? We need to carefully examine the evidence, gather insights from our experiments, and use our judgment to guide our search for those optimal hyperparameters.
I like that analogy. It highlights the importance of both analytical skills and a willingness to adapt and adjust our approach as we learn more about the problem we're trying to solve.
Now let's shift gears a little bit and talk about a more philosophical question. Given all these advancements and challenges, what do you think the future holds for machine learning? Where do you see the field heading in the coming years?
That's a fascinating question, and one that sparks a lot of excitement and speculation.
Yeah.
I think we're going to continue to see breakthroughs in areas like natural language processing, computer vision, and robotics. We'll see machines becoming more and more capable of understanding and interacting with the world in ways that were once thought to be exclusively human.
It's almost like we're witnessing the birth of a new kind of intelligence, one that's not bound by the limitations of human biology.
That's a thought-provoking idea, and it raises questions about the very nature of intelligence itself, right? What does it actually mean for a machine to be intelligent? How will these advancements in artificial intelligence impact our understanding of ourselves?
Mm-hmm. Yeah, we're getting into deep philosophical waters, but
Yeah.
but they're important questions to consider as we continue to develop these increasingly sophisticated machines.
Absolutely. We need to approach these advancements with a sense of both wonder and responsibility. We need to make sure that these powerful technologies are used for good to solve problems and improve lives. We need to be mindful of the potential risks and work to mitigate them.
It's like we're explorers venturing into uncharted territory. We're driven by this thirst for knowledge and a desire to push the boundaries of what's possible. But we also need to be aware of the potential dangers and tread carefully to ensure that our explorations ultimately benefit humanity.
Well said. It's a delicate balance, but one that I believe we can achieve through collaboration, open dialogue, and a shared commitment to using these powerful technologies for the betterment of society.
Now let's shift gears a little bit and delve into the fascinating realm of unsupervised learning. This is where we step away from the guidance of labeled data and embrace the challenge of uncovering hidden patterns and structures within unlabeled data.
It's like we're explorers venturing into a dense forest without a map. We have our senses, our intuition, and our tools to guide us. But the path is unclear, and the discoveries are waiting to be made.
It sounds both exciting and daunting. So what are some of the key tasks and techniques associated with unsupervised learning?
One of the most common tasks is clustering, which involves grouping similar data points together. Think of it like sorting a basket of fruit. You might group apples, oranges, and bananas based on their appearance, taste, and other characteristics.
So it's about finding those natural groupings in the data based on shared similarities.
Exactly.
Yeah.
And there are various algorithms for accomplishing this task, each with its own strengths and weaknesses. One popular algorithm is k-means clustering, which we touched upon earlier.
Right. You described it as finding optimal meeting points for groups of people based on their locations.
Exactly. It's like creating districts in a city. Each district has a center point, and people are assigned to the district that's closest to their home.
That's a very clear and intuitive analogy. So what are some other algorithms that are commonly used for clustering?
Another algorithm is called DBSCAN, which stands for Density-Based Spatial Clustering of Applications with Noise. It's particularly good at identifying clusters of varying shapes and sizes, even when there are outliers or noise present in the data.
So it's like identifying islands in an archipelago. Some islands might be large and densely populated, while others might be small and sparsely inhabited, but they're all distinct entities separated by the surrounding water.
Exactly. DBSCAN is particularly well suited for tasks like market segmentation, where you're trying to identify groups of customers with distinct needs and preferences.
Now let's talk about another important task in unsupervised learning, dimensionality reduction. As we discussed earlier, this involves finding a lower dimensional representation of the data that preserves the most relevant information.
Think of it like creating a concise summary of a long and complex document. You want to capture the key points without getting bogged down in all the unnecessary details.
No, it's about simplifying the data without losing its essence.
Exactly. And this can be incredibly valuable for tasks like data visualization, pattern recognition, and feature extraction.
We talked about PCA and UP as two popular techniques for dimensionality affection. Can you remind us how they work and what makes them different?
So PCA, or Principal Component Analysis, it finds the directions of greatest variance in the data and then projects the data onto those directions. It's like finding the most informative axes in a multidimensional space.
So it's like finding the lines that best capture the spread of the data.
Exactly. And by projecting the data onto those lines, we can reduce the dimensionality while retaining as much of the original variance as possible.
And what about UNIMAP-P? How does it differ from PCO?
UMAP, or Uniform Manifold Approximation and Projection, is a newer technique that often outperforms PCA, especially when it comes to visualizing high-dimensional data. It aims to preserve both the global structure of the data and the local relationships between data points.
So it's like creating a map that shows both the overall layout and the fine-grained details of the terrain.
Exactly. UMAP can create these beautiful and insightful visualizations that reveal clusters, patterns, and trends in the data.
These dimensionality reduction techniques, they sound incredibly useful. But are there any caveats or limitations that we should keep in mind?
One important consideration is that dimensionality reduction always involves some degree of information loss. We're essentially trading off some detail for simplicity. So it's really important to choose a technique that preserves the information that's most relevant for the task at hand.
So it's like choosing the right level of detail for a map, right? You don't want a map that's so cluttered with information that it becomes impossible to read. But you also don't want a map that's so simplified that it loses its usefulness.
Exactly. It's all about finding that right balance between complexity and clarity.
Now let's move on to a task that's particularly relevant in the context of unsupervised learning, outlier detection. As we discussed earlier, this involves identifying those data points that deviate significantly from the norm. They're like the rebels, the misfits, the ones who dare to be different.
Yeah. Exactly. And sometimes those outliers, they can be incredibly valuable. They might represent fraudulent activity, rare diseases, or unexpected breakthroughs, but they can also be noise or errors that need to be addressed.
So it's important to be able to identify and understand outliers to determine whether they're valuable insights or simply noise in the data.
Precisely. And there are several techniques for accomplishing this task. One approach is called one-class classification, which involves training a model to recognize what's considered normal, and then any data point that falls outside those boundaries of normality is flagged as an outlier.
So it's like establishing a dress code for a party. Anyone who shows up in something completely different from what's expected will definitely stand out.
Exactly. And that can be a good thing or a bad thing, depending on the context. Another approach is to use autoencoders, which we discussed earlier.
Right. Autoencoders are those neural networks that learn to reconstruct their input. So if we train an autoencoder on normal data, it's going to have trouble reconstructing any outlier data points. It's like trying to fit a square peg into a round hole.
Exactly. By measuring the reconstruction error, we can identify potential outliers. The data points that the autoencoder struggles to reconstruct are likely to be the ones that deviate most significantly from the norm.
These outlier detection techniques sound incredibly powerful. It's like having a team of detectives constantly scanning the data for anything suspicious or out of place.
Absolutely. And as the volume and complexity of data continue to grow, outlier detection is going to become increasingly important for ensuring data quality, security, and insightful analysis.
We've covered a lot of ground in our exploration of unsupervised learning. It's a fascinating area full of potential and challenges. But before we move on, I'd like to take a step back and reflect on the broader landscape of machine learning. What are some of the overarching trends and themes that you've observed?
Well, one prominent trend is the increasing democratization of machine learning. Tools and resources are becoming more and more accessible, making it easier for individuals and organizations to harness the power of these technologies.
No, it's no longer this exclusive club for data scientists with PhDs. Anyone with curiosity and a willingness to learn can dive into the world of machine learning.
Exactly, and this is incredibly exciting because it means that more people can contribute to the advancement of the field and to the development of solutions that benefit society.
It's like the printing press revolutionized access to knowledge. Machine learning tools and resources are doing something similar for the world of data and algorithms.
That's a powerful analogy. Another trend I've observed is the growing emphasis on ethical considerations in machine learning.
Right. We've touched on this throughout our conversation. As machine learning models become more pervasive and influential, it's crucial that we develop and deploy them responsibly.
Absolutely. We need to be mindful of potential biases, unintended consequences, and the impact of these technologies on individuals and society as a whole.
It's like we're not just building machines, we're shaping the future. And it's a future that needs to be guided by ethical principles and a commitment to human well-being.
I couldn't agree more. It's a responsibility that we all share as developers, practitioners, and users of these powerful technologies.
Now let's shift our focus to a specific area of machine learning that's been generating a lot of buzz in recent years: deep learning. We've already touched upon some of the key concepts and algorithms, but I'd love to dive a little deeper into the world of neural networks.
Let's do it. Deep learning is a fascinating and rapidly evolving field. It's like we're unlocking the secrets of the brain and using those insights to create machines that can learn and think in ways that were once considered impossible.
It's a bit mind-boggling to think about, but it's also incredibly exciting. What are some of the key characteristics that distinguish deep learning from other forms of machine learning?
One key difference is the sheer scale and complexity of the neural networks involved. Deep learning models often consist of millions or even billions of interconnected nodes organized in multiple layers.
It's like comparing a small village to a bustling metropolis. The scale and interconnectedness are on a completely different level.
Exactly. And this vast network of interconnected nodes allows deep learning models to learn these incredibly complex patterns and relationships in the data.
It's like they're capable of seeing the world through a much more nuanced and sophisticated lens.
That's a great way to put it. Another key characteristic of deep learning is its ability to learn hierarchical representations of data. Remember that idea of building a tower of knowledge.
Yeah.
With each layer adding a new level of understanding.
Right. We talked about that in the context of convolutional neural networks or CNNs. The early layers might learn simple features like edges and textures, while deeper layers learn to recognize more complex patterns like shapes, objects, and even faces.
Exactly. This hierarchical learning allows deep learning models to perform incredibly well on tasks that involve complex patterns and high dimensional data like image recognition, natural language processing, and speech recognition.
It's like they're able to decode the intricate language of the senses, to understand the world in a way that's much closer to how humans do.
That's a fascinating thought. And it raises questions about the potential for deep learning to surpass human capabilities in certain domains.
That's certainly a topic for another deep dive. But for now, let's focus on the practical applications of deep learning. What are some of the areas where these models are making a significant impact?
Well, one area where deep learning has truly revolutionized the field is computer vision. Thanks to CNNs, machines can now recognize objects, faces, and scenes with remarkable accuracy.
It's like giving machines the gift of sight. They can now see the world and interpret visual information in ways that were previously unimaginable.
Exactly. And this has led to breakthroughs in areas like self-driving cars, medical imaging, and security systems.
It's incredible to think about how far we've come in such a short time. Just a few decades ago, the idea of a machine that could see and understand the world was pure science fiction.
It really highlights the transformative power of deep learning. And computer vision is just one area where these models are making an impact. Another area is natural language processing or NLP.
Right. We touched on this earlier in the context of RNNs or recurrent neural networks. These models excel at tasks that involve sequential data like text or speech.
Exactly. Thanks to RNNs and other deep learning architectures, machines can now translate languages, generate text, summarize documents, and even hold conversations.
It's like giving machines the gift of language. They can now understand and generate human language in ways that are becoming increasingly sophisticated and nuanced.
It's truly remarkable, and these advancements in NLP are having a profound impact on areas like machine translation, virtual assistants, and chatbots.
It's like we're breaking down the barriers between humans and machines. We're creating a world where machines can communicate and interact with us in more natural and intuitive ways.
That's an interesting perspective, and it raises questions about the potential for deep learning to enhance human communication and understanding.
Yeah.
Right? Could these models help us to bridge cultural divides, translate complex ideas, and facilitate more meaningful interactions?
Those are profound questions that deserve further exploration. But for now, let's shift our focus to a specific type of deep learning that's been generating a lot of excitement: generative adversarial networks, or GANs.
GANs are a fascinating and powerful type of deep learning model that have the ability to generate new data that's similar to the data they were trained on.
So it's like they're learning to create, to become artists in their own right.
Exactly. GANs work by pitting two neural networks against each other. One network, called the generator, is responsible for creating new data. The other network, called the discriminator, is responsible for distinguishing between real data and fake data that's generated by the generator.
So it's like a game of cat and mouse, right? The generator is constantly trying to fool the discriminator into thinking its creations are real, while the discriminator is constantly trying to improve its ability to detect fakes.
That's a great analogy, and through this adversarial process, both networks get better and better. The generator learns to create increasingly realistic data, while the discriminator becomes more adept at spotting fakes.
So it's like a creative arms race where both sides are pushing each other to their limits.
Exactly, and the results are often stunning.
Mm-hmm.
GANs have been used to generate realistic images, videos, music, and even text. They're capable of creating art that's indistinguishable from human created art.
It's a bit mind-blowing to think about machines that can create. It challenges our very notions of creativity and what it means to be human.
It does, and it raises questions about the role of AI in the creative process, right? Will machines eventually surpass human creativity? Or will they become tools that augment and enhance our own creative abilities?
Those are fascinating questions that we can only speculate about for now. But one thing's for sure, Jans and other generative models are pushing the boundaries of what's possible with AI, and they're likely to play an increasingly important role in our lives in the years to come.
I agree. They have the potential to revolutionize fields like art, design, and entertainment. And they're also opening up new possibilities in areas like drug discovery, material science, and data augmentation.
It's an exciting time to be witnessing these advancements, but as we've discussed throughout our deep dive, it's crucial that we approach these technologies with a sense of responsibility and a commitment to ethical development.
Absolutely. The power of these technologies is undeniable, but it's up to us to ensure that they're used for good,
Yeah.
to create a better future for all.
Well said. And on that note, I think it's time to wrap up part 2 of our deep dive into the world of machine learning. We've covered a lot of ground, from the fundamentals to the cutting edge, and we've explored the challenges and opportunities that lie ahead.
It's been a fascinating journey, and I hope you feel inspired and empowered to continue exploring this incredible field.
I certainly do, and I'm eager to delve into the next part of our deep dive, where we'll continue our exploration of machine learning and discuss some of the emerging trends and future directions of this transformative field. Welcome back to our deep dive into machine learning. It's been quite a journey so far, wouldn't you say? Exploring all those fundamentals, going deep into neural networks, discussing the challenges and the exciting opportunities ahead.
Yeah, it really has. It's been a whirlwind tour, but I hope you're feeling a bit more confident and excited about the potential of machine learning.
Absolutely. And for this final part of our deep dive, I'd love to expose some of those emerging trends and potential future directions for this rapidly evolving field. What do you think?
That sounds like a great way to wrap up our exploration. Where would you like to start?
Well, the book talked about the increasing importance of explainability in machine learning models, especially now that they're being used for, more high-stakes decisions like loan approvals or even medical diagnoses.
You're right. The black box nature of some models, particularly deep neural networks, is a growing concern. If we don't understand how a model makes a decision, how can we really trust its judgment or hold it accountable for its actions?
Exactly. It's like imagine being given a verdict in court without any explanation or justification. You probably feel a bit uneasy or even distrustful of the outcome.
Precisely.
Yeah.
And that's why there's this push for more transparent and interpretable machine learning models where we can actually understand the reasoning behind the predictions. This is important not just for building trust, but also for identifying any potential biases or errors in the model's decision-making.
Yeah, it's like having a window into the model's thought process, right? We can see how it's weighing different factors and arrive at a more informed understanding of its decisions.
That's a great way to put it. And there are different ways to achieve this explainability. One way is to develop models that are inherently more interpretable, like decision trees or role-based models. These models make decisions based on a set of explicit rules, which makes it much easier to understand their logic.
So it's like being able to trace the model's decision path to see step by step how it arrived at a particular conclusion.
Exactly. Another approach is to develop techniques for explaining the decisions of more complex models, like those deep neural networks.
Yeah.
This might involve visualizing the models, internal representations, or identifying the features that were most influential in its decision.
It's like having a detective examine the evidence and piece together the clues that led to a particular outcome.
That's a great analogy.
Yeah.
And as the field of explainable AI continues to evolve, I think we'll see more and more tools and techniques that help us understand and ultimately trust the decisions made by these increasingly powerful models.
That's good to hear. Now, another trend that really stood out to me was the rise of federated learning. It sounds like a way to train machine learning models without without compromising data privacy, which seems incredibly relevant these days.
It is. Federated learning tackles that growing concern about data centralization and the potential for privacy breaches. It lets us train models on data that's spread across multiple devices or locations without actually having to collect all that data in one central place.
So it's like training a global model without ever having to gather all the data in one place.
Exactly. Imagine you want to train a model to predict text messages. Instead of collecting everyone's text messages in a giant database, which would raise a lot of privacy concerns, you could actually train the model on each user's device individually.
So the model is learning from the data on each device without ever actually seeing the data itself.
Precisely. Each device trains a local model on its own data and then shares the model's parameters or weights with a central server. The server then aggregates these parameters to create an updated global model, which is then sent back to the devices for further training.
It's like a collaborative learning process where each device is contributing to the overall knowledge of the model without ever revealing its own data.
Exactly. And this approach has a lot of advantages. It preserves data privacy, reduces the risk of data breaches, and allows us to train models on much larger and more diverse data sets.
It sounds like a win-win for both privacy and model performance. Now, another trend that's been generating a lot of buzz is the intersection of machine learning with other fields like biology, physics, and material science.
You're right. Machine learning is becoming this incredibly powerful tool for scientific discovery and innovation. It's like we're using these algorithms to unlock the secrets of the natural world and to design new materials and technologies that were previously unimaginable.
Can you give us some specific examples of how machine learning is being applied in these fields?
Sure. In biology, machine learning is being used to analyze genomic data, predict protein structures, and even design new drugs. In physics, machine learning is being used to simulate complex systems, analyze experimental data, and even discover new laws of physics.
It's like machine learning is becoming this universal language of science, helping us to understand and manipulate the world around us in ways that were never before possible.
I think that's a great analogy. And as machine learning techniques continue to evolve and as we gather more and more data, I think we can expect to see even more breakthroughs in these fields. It's a really exciting time to be at the intersection of machine learning and science.
I completely agree. Now, as we wrap up this deep dive, I want to touch on something that's been woven throughout our conversation, the ethical considerations of machine learning. As these technologies become more powerful and more pervasive, it's more important than ever to ensure that they're developed and used responsibly.
You're absolutely right. We've talked about the importance of data quality, explainability, and the potential for bias. But these are just a few of the ethical considerations we need to be mindful of as we continue to advance the field of machine learning.
It's like we're navigating uncharted territory. We have these powerful tools at our disposal, but we need to use them wisely with a clear understanding of their potential impact on individuals and society.
I couldn't agree more. We need to ensure that these technologies are used for good to promote fairness, justice, and human well-being.
And that requires ongoing dialogue, collaboration, and a commitment to ethical principles. We need to involve diverse voices in the development and deployment of these technologies and to ensure that their benefits are shared by all.
Absolutely. The future of machine learning depends not only on our technical prowess, but also on our ability to navigate the ethical challenges and to ensure that these technologies are used to create a better world.
Well said. That's a powerful message to end our deep dive on. It's been an incredible journey exploring the world of machine learning, from the fundamentals to the cutting edge, from the challenges to the opportunities. I hope you've enjoyed the ride.
Me too. And I hope you feel inspired and empowered to continue learning and exploring this fascinating field.
And to our listener, we encourage you to keep diving deep. There's a wealth of resources available online and through the book's companion website, themlbook.com. Keep learning, keep experimenting, and keep pushing the boundaries of what's possible with machine learning. Who knows, maybe you'll be the one to make the next groundbreaking discovery.
Until next time, happy learning.
And keep diving deep.